Section 21. Structure, galaxies, filaments, cosmic voids. Cold dark matter is believed to not interact with electromagnetic radiation. When matter dominated expansion, slight overdensities of dark matter expanded slightly more slowly than the universe's average expansion. Some of the overdensities were able to start contracting under their own gravitation, while ordinary matter was still a hot plasma in the first hundreds of thousands of years after the Big Bang. Some of these overdensities will later become the dark matter halos of galaxies and galaxy clusters. After recombination, slight overdensities of neutral ordinary matter, hydrogen and helium, were able to start contracting into clouds and then stars. The cores of stars reached high enough density, temperature, and pressure to fuse deuterium to helium and then hydrogen to helium. The stars shone brightly in visible and ultraviolet light. Whatever constitutes dark matter, it is believed to attract itself only gravitationally. Unlike ordinary matter, dark matter seems to have no way to turn its kinetic energy into radiated heat. It seems collisionless. Dark matter overdensities contract and condense, but seem not to collapse to a point or to the density of a star. Dark matter formed the large diffuse halos within and surrounding present galaxies. Cosmologists believe that individual stars formed before the galaxies formed. Smaller size before larger size. Later there would be discernible clusters of galaxies and then superclusters, each with a dark matter component. Cosmologists call this structure formation. However, superclusters formed late enough to not be gravitationally bound, with expansion now accelerating. Here are some of the superclusters and large cosmic voids in our neighborhood. The large cosmic voids are relatively devoid of galaxies, but presumably still contain diffuse ionized hydrogen and helium. I have not found any reference to the presence or absence of dark matter in cosmic voids. The universe is only homogeneous on a large enough scale, 100 megaparsecs, that includes both superclusters and cosmic voids. Do not think of the cosmic voids as being empty due to some repulsive anti-gravity. Dark energy does not repel in that way. Cosmic voids had lost mass to nearby superclusters' attraction. Here is a distant image of the cosmic web. Clusters and superclusters seem to have collected into long filaments, shown in green, bordering the cosmic voids, shown in dark blue, in this artist visualization. Here is a different artist visualization. Note the filaments and the voids. Condensation of superclusters and filaments is different than the condensation of a star, in that the expansion of the universe plays a significant role, as does the finite speed of propagation of gravitational information. Here is the result of a simulation of the structure formation of the galaxy filaments and cosmic voids. Nearly every galaxy is believed to have at its core a rotating supermassive black hole of mass several 100,000 to billions of solar masses. Cosmologists do not know when supermassive black hole precursors initially formed, but some may have existed when the first stars were formed, not from the merger of massive stars. Perhaps dark matter has a component that was clumpy at early times. Gas and shredded stars spiraling toward the black hole event horizon and accretion disk, shown here in red, yellow, and white, heats up and high-energy particles escape in two jets in opposite directions. This is one of the jets. Early in the life of a galaxy, the jets can be brighter than the stellar core of the galaxy. These cases are called quasars, or active galactic nuclei, AGNs. Over time, the immediate area of the black hole gets cleared out. More information is available in the course on gravitation and black holes.